Okay, so in this section what we're going to do is talk about parsing, which is taking a string which represents an expression and uncovering that structure, turning it into an Erlang expression. Now, we've seen that we can go in the reverse direction, that is, go from an expression to a string simply by doing recursion over the structure of the expression. But parsing is a bit more complicated. What we have to do is tease out from a string, just a sequence of characters, what the intended expression is. So, let's have a think. First of all, try and get our heads around what the types of a parsing function will be like. And here you see an example of applying parse to the example expression that we've been looking at all through this masterclass. But also you can see examples of us successfully parsing a number and a variable. So what we see here is we apply a parse function to a string, and what we get back is an expression. Okay, fair enough. But what about if we apply parse to something like the string which begins with 2, but also has some other content that's going to be of value? Well, this expression begins with a number, so the structure we can uncover there is the number 2. But there's a whole lot of other interesting stuff that comes after the expression we've discovered. So what we need to do is keep hold of that part of the string that's still to be processed. So what we decide is that we'll make our parse function take a string and return an expression that it finds at the beginning of the string, and then as a second half of the result, it returns whatever bits of the string it hasn't parsed. So for example, if we have the full expression, parenthesized expression 2 plus 3 times 4, what we get back is the expression representation of it plus an empty string. If we have the string with just 2 in it, we get back the number 2 as an expression plus the empty string. But if we take the example where we've got the initial parenthesis already consumed and we parse the string beginning with 2, then we get back the number 2, but we get back as well the remainder of the string plus parenthesis 3 times 4 and so on. So the result of the parse is the expression we find at the beginning of the string plus whatever remains of the string which wasn't consumed, wasn't chewed up by the parse function. So that's the type. And obviously, whenever you're writing a program, you want to get the type right before you start writing the program. People may disagree about whether that's always the way that we do things, and we may have a discussion about that in the discussion after this masterclass, but in this case, it's important that we understand the direction we're going in and that that's the type of the function we're going to write. Okay, now let's think about what happens when we parse that string that begins with the parenthesis, and it's the string, the example we've been using as a running example. What do we have to do to recognize that string? Well, first of all, we have to spot that it begins with a parenthesis. Then we spot there's an expression. The expression here is 2. We then spot there's an operator, which here is plus. Then we spot another expression that began with a parenthesis, and it's the bracketed expression 3 times 4. And then finally, what we spot is the closing parenthesis. And that's what we have to find. Parenthesis, expression, operator, expression, parenthesis. So that's the algorithm informally. What does it look like when we write it in Erlang? Well, here it is. You can see the comments that say what each line is doing. What I've done now is highlight the stages that we run through. So first of all, we pattern match as the argument on an opening parenthesis. So we match the parenthesis, and then the rest of the string gets passed to parse. We make a recursive call to parse because what we've got to spot is an expression. If we spot the expression, then whatever remains after that, we check to see whether it begins with an operator. So we do a pattern match here for an operator. And then after the operator, we parse again on what remains after that to spot another expression. And then finally, what we do is pattern match on the remainder having a closing right parenthesis. So you see the sequence there of the 4 pattern matches correspond precisely to parenthesis, expression, operator, expression, closing parenthesis. And the remainder of the string after doing all those parses is the second part of the result, and the first part of the result is the expression, where we do a case switch on whether we've spotted a plus or a times as the operator. So you see here we're threading through that remainder of the string. In another language you might hide this behind a monadic interface, for example, if you've heard of monads in Haskell. But here what we're doing is directly manipulating that data. And in fact, once you've seen this, it gives you an understanding. If you put a more abstract interface on top of it, a monadic interface, it gives you an understanding of what's going on underneath. But what we're doing here is deterministic, top-down, predictive parsing by spotting the various patterns that we expect to see in forming an expression. Now, what we've seen here is an example of a composite expression. But the things that we haven't looked at so far are what we do with integers and what we do with variables. And what I want to do is cover that next. So let's just take a quick look at parsing something like the string -123 closing parenthesis. What we spot there is the number -123, and there's some stuff left over. Or we spot a string that begins with the sequence of characters variable, and then there's some other stuff. What you can see here is in both cases, what we're looking for is the longest initial segment, longest sequence of digits or small letters at the beginning of a string. So in doing this recognition, we have this pattern of looking to see that the beginning elements of a string have a certain property, and we want to get the longest sequence where every element of that string has a property. Now what we could do is we could write separate functions for numbers and for literals, but what I'm going to do instead is use a higher order function, a function that takes a function as argument, to generalize that problem and solve it for both those cases and lots of others as well. So what I'm going to do is write a function called getWhile that takes 2 arguments. The first is a property, that is a function that takes a value and returns a Boolean. It takes a list of some type. What it does is return the list split into the initial segment where every element of that segment has the property we're looking for, plus the remainder. So we represent the property, as you can see here, as a function from the type T to Boolean. In the case here, the type we're looking at is a type of characters, but it could be any type, in fact. So this is general in 2 ways. It's got an arbitrary type T in here, so it's a polymorphic function, but also it's got a function as a parameter, namely the function that takes an element of type T and returns the answer true or false, depending on whether it's got the property we're interested in. So Boolean value functions represent properties, and what we're doing is looking for the longest initial segment with a property. So how does that look as an Erlang program? You can see here I've shown the property in green, and what we have as a body when we still have a non-empty list to split, we have a case split on whether or not the element at the head of the list has the property P. And that's the case P of CH, because P, remember, is a property but represented as a function that returns a Boolean. So we can do a case switch on that result. And looking at the false result first, what we do is simply return the whole list as remainder, and the initial segment we found is empty. Otherwise, if the first element, which we're calling CH here, has the property we're looking for, then what we do is a recursive call on the remainder of the list, and that gives us a list, 2 lists as a result, the succeeds and the rest of the list, the remainder. And what we do is return as a result that succeeds part with the character we just looked at as the head. So we've got that non-empty list of successes there with CH at the beginning, and then whatever we can match with property P in the remainder of the list plus whatever is left. So that gives us the general case, and obviously in the case where we've got an empty list, there's nothing to look for. So we've got this nice property that, as I said, is general in two ways. It's polymorphic, we can use it on whatever type we like, and also for whatever property we like. Okay, so we've seen the general function. What do we do in the particular case of recognizing literals? Well, literals are strings of alphabetics. I've called small alphabetics, in fact. And what we do is we first of all check that the first element in the string that we're looking at begins with a character, and then we want to get the longest possible segment that has that property. And in order to do that, we use our getWhile function, and we call it with the function isAlpha. And isAlpha is designed to recognize precisely what we want to find. And then, as a result, we return a tuple which says here we've got a variable, so the first element is var, the atom, and then we convert the string that we found from a list into an atom using the function list2atom. So we found a way of recognizing literals. But on the way to doing that, we've also built a very general function. It also allows us to recognize numbers. It also allows us to recognize any sort of initial segment of a list which has a particular property, and that's general over the property and of the type of elements. So in particular, we can use this for recognizing numbers. So that brings us to the end of this section on parsing. We've seen how we can, depending on the structure of the grammar, if you like, we build a recognizer that expects certain things. We do a case switch on the first character of the remainder of the input to decide whether we're looking for a number, a variable, or an expression. And then when we've decided that, we chew up enough of the string to find an expression, a number, or a variable. So we've shown how to do that. A bit more complicated. We're using a different form of recursion here. We're using the power of pattern matching again, and we've also seen that we can write very general functions that are general over the type of elements and over properties, because we can use functions as arguments. So we're building a property as a data value that is a function, and that's a very powerful approach. So that's the last of the formal sessions in this masterclass. We'll do one more session, which is some live coding, but as we close, what I wanted to say was a bit more about how you can take these ideas a bit further yourselves. What I'm going to do in the live coding session is talk a bit about simplification. So that's something else that we can do. But you can think of adding subtraction, of division, you could think of adding unary minus, so all sorts of different operations you can add to the expression type. You could also add local variables, setting the values of variables. So you could have a let operation, for example. You could also introduce functions into your expressions. You could add other types. So, for example, you could have a type of Booleans. You could also change the syntax if you wish. We've had a fully parenthesized syntax, but what you could do is add operator precedence so that you don't have to parenthesize an expression like 3 plus 2 times 4. You know that the 2 times 4 will bind first, and then the 3 plus afterwards. So lots of different directions to go in. And that's a good way of reinforcing what you've seen in this masterclass. Take those ideas further yourself. Okay, so that's it for this session.